Good fortune to go to graduate school with several people who became very, very prominent linguists. And one of these is certainly Bruce Hayes, our speaker today. Bruce finished his PhD in 1980 at MIT, and he has been a leading theoretician in phonology ever since. He's best known for the work that he has done on so-called metrical phonology, that is the phonology of stress. And a lot of the work that was done in the 80s and 90s in phonology on stress, and there was a lot of emphasis on that particular area of phonology, was actually due to his work, and actually took his work as a real model for both the great theoretical depth of his work and also the breadth of empirical coverage. Concern as it was with developing a well-formulated typology of stress systems. Bruce Hayes has also worked in other areas of phonology, especially in recent years. He has worked on acquisition, on the acquisition of phonology, and he has also worked on the trying to capture the numerical or the statistical basis of knowledge of phonology and morphology. Am I leaving anything out? He has also developed software. He has a bit of a mathematical background, so he is a real specialist in metrical phonology, but an intellectual of considerable breadth. Bruce?
Thank you, Luigi. How could I possibly live up to that? You all have handouts? You're lost without handout. Okay. Here. First, acknowledgments of my collaborators. This, from almost the very beginning, has been a roughly equal collaboration between myself and Adam Albright of UCLA, who's a graduate student in the linguistics program. When I say almost equal, I imply probably the majority is his. More recently, two other graduate students, Argelia Andrade and Stephen Wilson, have been joining us on the project. The past tense controversy originated on or about 1986 with the publication of Rumelhart and McClellan's simulation of English past tenses using connectionism. The idea was to get a simulation that would predict English past tense forms from the present form by learning from a data set. Okay? The system works to the extent that it works without the use of any symbolic rules such as a linguist might want to posit. And it's coupled to a certain amount of ideology, in particular skepticism about the need for symbolic or rule-based approaches to linguistics, like generative grammar, or cognition in general. Okay, so it made quite a splash. A perhaps almost equal splash was made by Pinker and Prince's reply 2 years later, 120 pages of mostly critical commentary. Their claim was that the Rumelhart-McClellan system fails most conspicuously in areas where one would need rules to succeed. Forms like, say, plumph, where there's no good model in the existing lexicon, and the only way you could derive the right past tense, plumphed, would be to employ a general rule. On the other hand, their paper was not entirely critical of the work. They noted with enthusiasm the new empirical domain for research that Rumelhart and McClellan had pointed out, namely the puzzling quasi-analogical family resemblance relationships among irregular verbs. Verbs that are irregular but pattern the same, like keep, kept, leap, leapt, or grow, grew, blow, blew. Okay. From this initial intellectual clash, opposing schools of thought have emerged. The so-called dual mechanism model propounded by Pinker and Prince and elaborated on in a truly enormous subsequent literature, says the following. Regulars are generated online by a single default rule, like add the suffix -ed. Irregulars are memorized, but they can also to some extent be formed analogically through the use of a associative network. Later versions of the model alter these a little bit.
This is what Pinker said.
Yeah. And later versions of the model have altered these views, but that's the scheme. Connectionists, in turn, have argued that with technical improvements in the way the simulation works, the system could be made to work quite a bit better than Rumelhart and McClellan's system. Therefore, no fundamentally reconceived system involving, say, rules is needed to model people. And I give you various references there. Okay. Now, what I'm going to talk about here. The group I'm working with at UCLA has our own approach to past tenses and morphological learning, which is different from either of the two that I've described here. And that's going to be most of the talk. I'll tell you what we've been doing. But once I'm done, I will talk about implications, if any, of our work for the dual mechanism theory and implications for connectionism. So that's the plan. All right. The original goal in setting out this project was to develop a machine-implemented algorithm for learning morphology and phonology. We wanted, of course, to model the process of phonological and morphological acquisition. And we also wanted to test phonological theories for their learnability consequences. Maybe some of them would make language learning easier. Some might turn out to be bad proposals because they make learning harder. Okay. In this, we're following work of Gildy and Jurafsky. To narrow the task to something that seemed feasible, the paradigms that are learned are limited to two-column paradigms. You're given data pairs, like, say, for English past tenses, jump, jumped, rub, rubbed, miss, missed, act, acted. And the system learns a grammar from these pairs, which, if you give it a novel form of category 1, a made-up word, say, it will project its guesses for the past tense category 2. For phonologists, it's worth noting that this system does not use the underlying form of the stem. It simply tries to project the past tense from the surface form of the present, following, for instance, work of Luigi Burzio, proposing phonological grammars that don't have underlying forms. Now, if you have a grammar, how do you know whether you're on the right track? The empirical testing is to submit the grammar to a so-called WUG test. A WUG test is a test where you give it a completely novel made-up verb and see what it does with it. Okay? Invented by Burko in 1958, who WUG tested small children. Then you WUG test native speakers of English, say, with the very same forms, and you compare. Okay? So currently, we've got undergraduates parading into the sound booth to take a WUG test. They see on the screen a sentence with a blank line, and they hear my voice saying, next week, we're going to Spling. We've been waiting ages for the chance to Spling. And then they read a sentence filling in the blanks. They say, we're reading a book about splinging. My friend, they pause to think about it for a sec, and they say, my friend splinged once, my friend splung once, my friend splang once. You get all these answers. Okay? But this will be my first time. Okay, so that's the WUG test. So then you compare what the model is doing with what the people are doing, and if there are differences, that indicates that you ought to revise the model or the theory of grammar that it presupposes. Now, there's a different way to test these kinds of grammars, and this is a way that we reject, despite the fact that it's quite a bit easier. You learn on half the corpus and you test on the other half. We think this is wrong because we're not trying to model a data corpus. We're trying to model people. All right? Moreover, if you think about it, there are forms in which the wrong answer is the right answer and vice versa. It is true that the past tense of think is thought, but if you had to synthesize the past tense of think, if you'd never heard it before, you would never guess thought. You would think thank or thunk or thinked. Okay, so that's why we put a lot of effort into the WUG testing. For this learner, we initially thought of two possible strategies. One would be to take classical phonology problems from linguistics textbooks, which can be quite intricate, but are always free of lexical exceptions. The rules, once you find them, always work perfectly, right? Okay. The other possibility would be to take on larger data problems with larger learning sets in which there are exceptions and try and learn in the presence of exceptions. And after I wrestled with my conscience, Adam Albright eventually persuaded me that we should take on the more realistic goal of large data sets with exceptions. That's real life. Well, why are exceptions hard? I think it should be fairly obvious. If you're going to formulate a rule, you have to factor out the exceptions. But of course, you don't know what the exceptions are in advance. You can only do that when you know what the rule is. Moreover, this makes it a bit harder still, I think. The exceptions aren't really just exceptions. It's been observed by Pinker and Prince and quite a few other people that they fall into families. that I mentioned earlier, in fact. Keep, kept, leap, leapt, sleep, slept, creep, crept is one family. You might think that that could just be another rule that overrides the general rule, but that's not true. There are exceptions to the exceptions in terms of forms like reap, reaped, not reap, wrapped. Okay, so what it really is competing generalizations, a very broad one and a narrow one. And you've got to learn both generalizations, despite the fact that both suffer from counterexamples. Okay, all right, how do we do it? We are inspired by a section not very well remembered right now, but actually we think quite important, of Pinker and Prince's paper that I alluded to earlier, which is an outline sketch, never implemented as far as I know, but an outline sketch of how a rule learner might work. So here we go. Entertain and test many hypotheses, because you never know in advance what will pan out. Okay. And the starting point, where do you get hypotheses from? You get them from the lexicon. This is an instance I mentioned this morning of bottom-up learning. Take each learning pair, like say you're given fling, flung, and construe it as a tiny, tiny little rule. Fling, flung can be construed, if you factor out the changing part from the context part, it goes to when it follows a word initial fl string and precedes a word final ing string. Okay, that's a tiny, tiny rule. That, of course, isn't going to get you very far, but it can serve as the starting point for generalization. If two micro rules have the same structural change, then you can combine them to form a new, more general rule. The method followed is to maintain all shared elements of the context, but reduce anything that's not shared to variables. Okay. Moreover, in doing this, we follow a principle of minimal generality. Never generalize beyond the point needed to match the input data. Okay, so let's take a look. Suppose you now have two pairs, fling, flung, ring, rung. Each spawns a micro rule. I goes to in such and such a context. These micro rules share a structural change, so you generalize. I goes to after a liquid, that's what L and R have in common, which is not necessarily initial before a word final ing. That's the minimal generalization that our template permits. Notice a supra-minimal generalization would be I goes to anywhere, and we don't do that. Clear? Right. Now, this is an incredibly stingy method, right? It is minimal, it's stingy. The way you can get general rules from it, however, is by digesting a larger amount of data. If you iterate the procedure, comparing each new learning datum with all existing pairs and rules, you will ultimately get a large rule set, which will have in it some very general rules. So here's an example. Suppose you're trying to learn the present participle of English, the stuff which is completely regular. You always just suffix ing. From grow and growing, you would find that the sounds grow and hiking, grow and hike, growing, hiking. You would find that O and K have almost nothing in common. They're both non-nasal, for what it's worth. So you get this little intermediate rule, attach ing after a stem that ends in a non-nasal, but the moment you consider a stem that ends in a nasal, like run, running, that will fix the problem, and you'll now have a rule that attaches ing anywhere, which is correct. Right. Okay. Now, how does learning terminate? Here is where we part company with Pinker and Prince. Their goal was, in fact, to discover the rule that is most general. So you iterate the above process until you find the most general rule. Generality is defined as follows, and this is crucial. It is the number of forms that the rule correctly derives. Note that it ignores the number of forms where the rule applies and derives the wrong output. We're only interested in finding the maximal number of hits, as it were. Okay? And then once you do this, you throw away every single intermediate stage rule that's less general. Okay, it's like you fill the workbench with thousands and thousands of rules, but at the end, there's a clean sweep. The remaining rule is plated in gold and mounted on the wall. Okay, our own approach is that it might not be right to discard all of these intermediate phases. Some of these intermediate rules could be quite useful. We can use them to good effect, we think, if you find the right way to evaluate them. So let's think about evaluation. Our guess, based now on some experience dealing with data, is that rules should be evaluated for how well you can trust them. How much can you rely on this rule? And trusting is extremely simple. Computer statistic we'll call raw reliability. It's the number of rules for the forms in the data set where the rule applies successfully, divided by the number of forms that meet the rule structural description. So it's hits over scope, as it were. Now, that needs a slight refinement. Suppose you had a rule that only applied to 5 forms and worked for all 5 of them, and you compare it to a rule that applied to 1,000 forms and worked for all 1,000. Surely we would give more credence to the rule that applies 1,000 out of 1,000. So we do this by making a statistical adjustment following work of Micheev, deriving a number that we'll call adjusted reliability. It is simply the lower statistical confidence limit on raw reliability. If you use a 75% lower confidence limit, 5 out of 5 is demoted from a score of 1 to a score of 0.825. 1,000 out of 1,000 is demoted from a score of 1 to a score of 0.999, which we think is intuitive. Okay. Last little bit in the basics. You now have a grammar. It's got possibly thousands of rules in it, and each rule has its own score for how good a rule it is. Now, I said that we test this system empirically by giving it a WUG test. How do you take the WUG test? The scheme is in 22. Input a WUG form, find all the rules that can apply to the WUG form, and apply all those rules. Of course, many of the rules will derive exactly the same output. How do you rate the output? The system is the score for the output. It's, as it were, well-formedness intuition for that output is the adjusted reliability of the best rule that derives it. Make sense? So every form is derived in the best way you can derive it. That's the scheme. Okay. Further details, let me run through this quickly. Our phonological representations are admittedly crude. They come from sound pattern of English, and they consist of segments that are bundles of features. Okay? Moreover, our theory of structural descriptions is a little bit crude, too. You can surround the context with literal strings of segments, partially specified feature matrices, and a variable indicating non-adjacency to word edge. This limits us in the problems that we can solve, because for fancier stuff, you need things like tiers, syllables, feet, et cetera, et cetera. But we think there still are data problems out there that are worth addressing, even with this limited resource. Yeah, question?
Going back to your rules that you're creating, how is it ever possible that you can have a rule applying two rules apply to the same one word? The way you're creating a rule, every rule can only apply to a single context, but to a single, and for every word that you input, only one rule will apply.
Oh, to the contrary. Often hundreds will.
There are no derivations of length longer than 1.
Oh,
Oh, wait, what?
is that it?
What was it that I said?
But there are no derivations of length longer than 1 in the system, right? You're talking about rules applying to the output of the
No, competition for application.
Right.
Rules on
It's
one.
not the way you're originally starting your rules, that you start with the most specific. So if you're, when
Oh.
building up more general rules, sort of excludes you from overlapping any existing rule, then how is it possible
Oh,
that a new
look,
rule?
make a distinction between learning and using the grammar. In learning, you build up generality one step at a time. Once you're done, you have a great big grammar. You take it home and you use it. And that means that you could apply all of the rules at once and collate their outputs and so on. Does that make sense?
Yeah, which rules do you throw out?
I haven't thrown out any rules at all. I kept every last one of them.
I think what is confusing is that in your examples you have like 1,000 out of 1,000 and 5 out of 5, but in fact, like what you want to say, I guess, is that it doesn't. So a rule doesn't always apply 100% to the things that it can apply to, right?
Uh-huh.
So some candidates for a regular ED rule are going to have irregular
That's right.
instance, right? So it would be like the ED rule generality would be something like 900 out of 1,000 or something like that.
Yeah.
Right?
That's pretty close to the real figure. Does that help?
Well, it would help if I understood it.
Well, that's what I meant.
So I go. So I don't understand this applicability of a rule, you know, I mean, so I give it an example, and this, sorry, I want to apply it to a particular situation. That situation has conditions which can apply to several rules. Is that right? I mean, that's a possibility. In other words, your rule is if so, if, and if, then such and such, something like that. And these if cases, in a particular instance, there are several rules which have if cases that apply.
Mm-hmm.
Is that possible?
Yeah.
Yes. So, and they each could have a different output.
Yes.
So how do I decide now?
Oh, the grammar actually is deriving several different outputs.
Yeah.
And we claim this is empirically necessary because people, on reflection, typically consider that several possibilities are available for the past tense of a novel form. So just as real humans say, yeah, it could be splinged, it could be splung, it could be splang, and we have numerical data on this, so should an algorithm say, yes, it could be splinged, it could be splung, it could be splang. And it should have numerical measures of how confident it is that it could be splang.
I see. And we take the view that if you're born in this country, you're privileged, and no matter how ignorant you are, that's fine. But if you're born somewhere else, then you just don't understand the language. Well, I mean, in other words, could it be that
What the hell
native
are you
speakers
talking
are not, that native speakers are not sure because in fact there is a deeper way of understanding the language and there is a shallower way, and
Yeah.
just being
Well, look,
more
I
ignorant
just
is-
adopt the standard ideology here of linguists, that the testimony
That's
of
why he's
the testimony of the native speaker reigns supreme. It is not our job to tell the native speaker what to say. The native speaker,
Polanski and
the native
you
speaker
are
is a source
equally-
of data, and our goal is to model the native speaker.
Bruce, however, with a real verb like spring, then how does the speaker select the right rule?
Oh, for a real verb, I suspect the speaker very often retrieves the correct form from memory. We are modeling the cases where the native speaker is obliged to engage in synthesis. And a word test is the clearest case of that type.
Yeah, but what's so confusing is that if you can see that the speaker is just retrieving it from memory, then what work is the generative system that you're developing actually doing? Is it sort of like complementary to the memory, or is it?
Can I take that on the question period? I think that, yeah. Okay. But I want to make sure things are reasonably clear before I move on. Okay, how the system works? Okay. All right.
So you convert the numbers into some response scales for the subjects? You get
Yes,
numbers-
we cannot expect that the scale used in the word test and the 0 to 1 scale of the model are going to be exactly the same scale, so we compare them by doing a correlation, as you'll see. Okay. I am going to skip phonology. Those of you who are phonologists, rest assured that there's a phonology in here, and there's a very clever way of discovering. I won't have time if I go through that now. Okay, let me give you some applications. First, English past tenses. We borrowed from Brian McWhinney's website a corpus of present past pairs in phonetic transcription. We augmented it to include all of the irregulars, and we fed it to the algorithm. It learned a grammar of several thousand rules. We then wug tested this grammar using 60 forms taken from the work of Prasada and Pinker, who did a very nice wug test in 1993. Then we did a correlation. The judgments of the learner, derived in the way that I told you, with the judgments of the native speaker consultants of Prasada and Pinker. The correlation we think is reasonably good. It's 0.75. Significance testing on the correlation indicates that it is pretty unlikely that the correlation is this good by accident. Yeah, you really want to ask a question?
Yeah, because you mentioned correlation. It seems to me that the test you use, this WOOC testing and the algorithm, they are very correlated somehow. I mean, you said that if you present things to a speaker and he doesn't know that thought is the past tense, he would come with something different, not thought. So somehow, I mean, these rules and these artificially created words, somehow this algorithm would work for that, but it seems to me that would not work for the real keys when you have real language there. And you'll not discover think thought with this, but you will discover.
Okay, well, look, I've been through this before. The purpose of doing an artificial verb is to show what people do when they are forced to productively synthesize a past tense. If you use existing verbs, there is the peril that they will be extracting it from their memory. Okay?
True, but
So this is the only test that I could think of that might legitimately test the hypothesis. We are trying to put our hypothesis to the most stringent test we can, and this is the only way I could think of. What can I say?
I don't know, I was
Yeah.
just curious what this
Okay.
would be gonna be.
All right.
We have another real test.
It might be useful for you to look at some numbers that are generated by the learner. For Cleed, its favorite is Cleeded. This is under 27. The rating of the learner is 0.913. It also guesses Cled, but not as good, 0.607. And then way down at the bottom, it has some guesses that would be perturbing if they didn't have such low scores. Cleed, today I cleed, yesterday I cleed, with 0.045. Today I cleed, yesterday I cleat, with 0.011. Looking at the production probabilities in the Prasada-Pinker experiment, we find that things look, I think, reasonably good. These numbers don't add up to 1 because they were allowed to guess more than one form. Cleated volunteered by 0.83 of the consultants, 0.42 for Cled. Likewise for Splinged, 913, Splung 786. Splang I think is a little bit low at 189, and Splot is reassuringly down there at 0.055. Okay. In another study, this one done by Adam Albright as his MA work, we looked at the question of projecting the conjugation class of Italian verbs. Okay. Here, there are 4 conjugations that you could see with the infinitive suffix are, ere, stressless ere, and ire. The task is to take the first singular present, which is often, though not always, ambiguous with respect to conjugation class. It's just an o, and project from it the infinitive. The idea is that Italian speakers can discern patterns in the phonological shape of the root. Okay, and these are used to project and guess what will be the conjugation class and hence the infinitive ending. Okay. Learning basis was about 2,900 Italian verbs from existing corpora. The WUG test was taken by the learned grammar and by 27 living, breathing speakers of Northern and Central Italian for 40 WUG verbs. Okay, and this was done, is kind of cute. Adam did it with a computer. You see on the screen, oggi rabado con mio fratello, which means I'm rabbidating with my brother today. And you hear a voice say this sentence. Then you rate 4 possibilities, mi piace rabadare, and dere, and dire, okay, on a 1 to 7 scale. And those all mean I like to rabidate. Okay, here the agreement of the grammar with the consultants was pretty good. It was about 0.792. Right? Moreover, Adam did a cluster analysis. He did a cluster analysis trying to see the relations of similarity among the consultants. And the cute part is if you look at asterisk predict, that is the computer model. And as the tree diagram shows, it is smack in the middle of a tightly knit cluster of similar intuition patterns. Okay? So the idea would be that you can't tell the difference between the model and a representative speaker. The last study I'll mention was kind of going out on a limb. We wanted to try to model the propensity of Spanish mid-vowels to diphthongize. The pattern here is one in which e and o are realized as ye and we whenever the stress rules put the stress on them. Thus, sentamos, siento, podemos, puedo. This is a minority pattern. Probably about 9/10 of the cases don't work this way. So you get rentamos, rento, podamos, podo. Now, in fact, there's every reason to think that this will be just a mess in terms of trying to predict it. It's there in the language because centuries ago in Proto-Romance there was a distinction between e and o and o, and it was only the e and o that diphthongized. So it's just total historical crud left over from centuries ago, in principle not predictable at all. Nevertheless, the little generalizations that are there in the data, essentially by accident, do appear to be apprehended by speakers of Spanish. We did a WUG test for Spanish, rather similar to the Italian one, though perhaps more cagily arranged. The consultants were given a verb like leramos, which means we lure, and they first filled in a number of blanks that were there just to make sure that they had heard it right and to give them practice in internalizing it. Okay? Then the crucial case is one at the end of the little dialogue they read. It's been 6 months since I, and in this case you use the present tense, I not lure. And what they would give us, of course, is either lero or liero. Okay? So here again, you get a correlation somewhat lower because we were stretching the method to its limit. But the production probability observed in the consultants' forms correlated against the prediction production probability obtained by weighting the learner's well-formedness scores. You get 0.510, which again is significant. So what do we have so far? It looks like this method is yielding grammars that behave, at least to the extent that we've been able to test them, in ways similar to the way that people behave, which is what we're trying to do. Now, do you want to ask questions now? I mean, this seems like a dangerous thing to ask, but is it clear at this point?
What's the differentiation supposed to correlate with?
You take the fraction of the time that the consultants volunteer to diphthong.
Yeah.
Then, using the method in footnote 2, you take the share of the total well-formedness scores for diphthongization and let that be the computer's fraction of the time, and then you correlate the two. That's how we correlate a production probability against a well-formedness intuition. Okay.
Just the number of times that the speakers will spontaneously diphthongize compared with the percentage that the diphthongization is present in the lexicon?
No, it's the lexicon has been left behind long ago.
Right.
We're talking about behavior of a grammar versus behavior of speakers.
So could I just, I see the correlation, but that could come from diphthongizing X number of, 20% of the time or 0% of the time, right? So, or not 0, but a small percent. It just needs to be the same small percentage that your model gets. So what
You mean if you guess diphthongization at random 20% of the time?
Random, just for a very small percentage of the. So if overall this, if your subjects opted not to diphthongize, but there was a small cluster of items that they did diphthongize for, right, on a reliable basis, then your correlation would be high. Wouldn't it? It would be that same cluster that your model came up with. I'm just wondering overall how often did they diphthongize?
About 20%, I think.
20%.
Yeah.
And your model?
I better not answer that. I can't remember. I can send me an email and I'll look it up for you.
I just want when
But
part of
there wasn't an answer to that question because all you have are a scalar ranking of alternatives and not a percent prediction, right?
but we're deriving that by dividing the diphthongization rating by the total rating.
For the model?
You have some percentage of the world verbs that your model says ought to be diphthongized.
Actually not.
Oh, no.
Non-diphthongization is always ranked better by the model than diphthongizing, but the crucial thing is that
There's differences based on the shape of the stem. And those are what's creating the correlation. Does that make sense? Okay. Now, I wanted to talk about two things. One is things that we think we've learned by doing this. So they're kind of questions internal to our model. And then, if time, I'll come back to remarks on the dual mechanism model and connectionism. Here's the theme. An adequate learner should be prepared for a variety of distributional patterns in the data. Some thought patterns have a shape that could stymie learning if your algorithm isn't arranged appropriately. So let me try and explain what that means. I'm going to do two cases. Suppose, as in 37, you have a general pattern. Okay, it's something that works most of the time. But inside it, you have a small specific pattern which is exceptionless. Okay, what are you going to do with that? All right. Internally exceptionless. Okay, so one such candidate, if you look in a dictionary of Spanish, you will find that every one of the 11 verbs of Spanish in which e precedes a trilled brr, every one of them is a diphthongizer. Okay, and they're listed there. So that's exactly this kind of case. The normal pattern is not to diphthongize, but the specific pattern is to diphthongize in er verbs. That's the scheme. On the other hand, we did this one test, and we included two verbs that have this shape. Leramos, we ler, and derramos, we der. Okay? And the data that came back, only 20% of the consultants diphthongized in leramos to liero, only 21% to diero. Okay, so what's going on here? A couple things that you could find. One conjecture, though, is that the general pattern, which works like 9 out of 10 cases in lots of data, is overriding an exceptionless pattern, simply because of the great difference in size. We admit that there's other possibilities, the fact that the general pattern involves no alternation. But that's, this is the sort of case that we're interested in. Okay, so small exceptionless pattern overridden by a very large general pattern.
Excuse me, let's see if I understand. I mean, somebody who is in favor of rules would say that there is a clear rule in Spanish that's such and such, the one that you just described.
Yeah.
And here we would have human beings who don't recognize it, shall we say.
Right.
So, would you take this as an argument that in fact there are no rules in language?
I think that'd be pretty extreme.
Well,
I think it's,
okay, I went there too far.
I
But
think
those who feel that there are rules,
I
you
would
know,
see
are
this.
now
Okay.
on very shaky ground. Because
No,
after
no.
all, if humans can't.
I think it's actually a rational response to trust the bigger generalization. But to put it more generally, you could say we are engaged in an empirical investigation to see how people behave in a learning situation of this type. Now, the fact is, they responded with diphthongs more often than they did in cases that don't have good rules.
Yeah, but that just shows that people behave statistically and not by rule.
Well, this is a model in which people behave both ways. They are behaving by rule, but the applicability of the rule is determined statistically.
Could it be that people learn exceptions and then they are reluctant to agree with other exceptions in that language? Because these verbs look like, I don't know, 11 you mentioned, exceptions. And then you'd say, is this one of those? And then you try to apply just the general rule because you learn that you have those exceptions.
That would be a different theory.
And this kind of theory, I guess, wouldn't explain why still 20% of the time they agree with new exceptions. and spontaneously produce new exceptions.
Yeah, that's a good answer, actually.
Are you 100% comfortable with this particular Spanish example, or do you have others that also make the same point? A closed, perfect set?
This is the prettiest one.
Yeah.
I'm a little worried that all Spanish speakers don't have the same pattern. You know, this is what you'll see in the dictionary, but are the living, breathing
I'm
speakers.
a little uncomfortable with the fact that it sort of patterns with de as a prefix, and then a verb like derramar and so forth. No?
Well, there's
Just
I
a
think
possible.
usually stems in Spanish have at least one syllable. So,
Right. I mean,
derro, yeah.
okay, if you're comfortable with it, then.
Okay. All right. Now, we actually, the goal was, let us suppose this is right and see what might be interpreted theoretically from this. There's a whole research program quite active in using optimality theory for phonological learning. Is initiated in work by Bruce Tesser and Paul Smolensky. The scheme is this. You are given an inventory of phonological constraints, and you're given a batch of data. The learning algorithms of the type first proposed by Tesser and Smolensky take the data and then arrive at a ranking or prioritization of the constraints. And the result is a grammar. And if people have picked up on this idea and attempted to formulate algorithms that can handle different ranking tasks. Now, of all the algorithms that I've put in the first bullet in 38, they all share one crucial property. If you have a constraint that is never violated in the learning data, it gets ranked at the top of the grammar, okay? Right? So any constraint that works perfectly is always ranked on top. But this looks like a fatal consequence. Suppose we found some way to translate the generalization about into optimality theory, which strikes me as pretty feasible. Any one of these ranking algorithms is then going to put that constraint at the top of the grammar, and the non-diphthongizing constraint, whatever that will be considerably subordinated. End result, the grammar would guess dierro and liero all the time, okay, which is a fatal error. So what's going on here? What I think is going on is that the constraint diphthongized is a parochial constraint. We got it not from some general theory of phonology, but by looking at the lexicon of Spanish. If we are going to get constraints by looking at the lexicon, then here's the little motto, third bullet. Inviolability cannot diagnose undominatedness. That's the scheme. So indeed, it's when we hit this problem, and we hit it in a very major way in earlier versions of the learner, we made a somewhat radical decision, despite my being an ardent fan of this theory and thinking that it's fundamentally right in certain respects. We threw it out. Okay, so it's an OT-less learner. And to bring it back, I think we should bring it back, because it would offer facilities for bringing in tendencies like phonetic naturalness and avoidance of alternation into the system, which at present are absent. Okay. To do that, we need a more flexible version of OT, for which we think the recent proposal of Zura is a good candidate. But we also need something that hasn't been invented yet. That is, a learning algorithm for that version of OT, which crucially downgrades generalizations that are sparsely manifested. Okay, so something that works perfectly, but only 11 out of 11 times, you shouldn't take it that seriously. All right, and it should be subordinated in the grammar. Okay, that's a simple case where looking at the data pattern suggests changes in phonological theories. I have a more complicated one, which is in 39. Intuitively, it involves generalizations that are shaped like a schoolhouse plus a flagpole. Now, what do I mean by this? There are hundreds of verbs in English in which the past tense suffix is pronounced as T. things like jumped, talked, missed, crashed, laughed. And of course, like most English verbs, they're mostly regular in our corpus, 380 out of 414. Then, depending on the dialect of English you speak, there is a certain number of, all of these verbs where it's regular end in a voiceless consonant, like T or P or S or whatever. In addition, depending on the dialect of English you speak, there's a small number of verbs that end in a voiced sonorant consonant, like L or N. I personally command only dwelt, though I passively recognize spelt, smelt, spoilt, spilt, burnt, and learnt. Okay. Moreover, if you take that T and add in some phonology, it is easy to make the rule perform even better. You can turn the T into D if it follows a voiced obstruent. You can add a schwa before it if it follows an alveolar. This would produce, well, here we go. Here's the scheme. Look at the schoolhouse only. For the schoolhouse only, you can get a rule that works quite well. It's attach T after an obstruent. Right? Here's the problem, though. Suppose you add in some flagpole forms. Now, if you do the flagpole forms and do minimal generalization in the way that I described, you get a new rule. And the rule is going to be like this. Attach T after any consonant. All right. Well, that rule statistically doesn't look all that bad. It succeeds about 65% of the time. And the rule can be visualized by looking at the smaller diagram with the dotted lines included. The existence of this small number of irregular verbs spawns a more general classification in which the T can be attached to all consonants, not just the obstruent subset. This generalization is fatal. If you look at a schoolhouse with a flagpole and decide that what you see is a uniform rectangle, you are going to grossly overgeneralize. In particular, you will find it reasonably good to attach T to any consonant stem. And the prediction is that if you asked speakers, what's the past tense of lan, they'd say, well, land, of course, but lamp sounds pretty good as well. Okay, which I think is preposterous. We'll have data on that pretty soon. We discovered this, of course, the hard way by having a learner that fell into this trap as soon as we put a form like burnt into our learning data. We now think we have a way out of the trap, which I won't have time to do in detail, but let me just tell you very quickly how it works. Every rule gets a lowered adjusted reliability score if it fails to outperform all available subset generalizations. Intuitively like this. The large rectangle with the dotted line does not outperform its subset, namely the school. In fact, virtually all of the data for which it works is within the school. So adding the enormous amount of territory of the sonorant consonants it only gets you a few additional good cases like dwelt, but it adds in zillions of cases where the rule fails, like, say, expelt. Yeah, Luigi.
Wouldn't the overgeneralization be actually killed by the fact that you have many cases that actually contradict the extension? So you have build with a D. Wouldn't that be sufficient to?
Well, what's at issue is how do we ensure that those cases will kill the large generalization? Okay, so just very briefly, you subtract out the schoolhouse from the large figure, and what you're left over with is a horrible rule. And that is the crucial diagnosis. Okay, so that's what we're doing. One last bit, I better start skipping. But there's an implication for the original algorithms proposed by Pinker and Prince. If you'll recall, the way they measure a rule is simply to count the number of cases where it works. And we take this to be fatal here. because you can have a rule that attaches to t, It works in a few hundred cases, but it's limited to obstruents. If you add in cases like learnt or burnt or spelt, it will add 2 or 3 more hits. And suddenly, the best rule defined by their criterion is the one that attaches t after any consonant. Okay, so we take this not just to be evidence that we needed to change our model, but that the Pinker-Prince model could not possibly be right.
Excuse me.
Yeah.
Sorry. Just so, it is the best rule if you only if it only competes with attached D, right, or attached D. But if it competes with attached D and then the voice, which is already a rule that exists, then attached D and the voice is a better rule, right?
Let me think. Possibly. Yeah. I hadn't thought of that. Thank you. Yeah. I won't try to think on my feet about that one. That's a good point. Okay. All right. Let's go back to the original business about the past tense controversy. To review, the dual mechanism model says that there is a single, typically very simple default rule, and it's used to derive regulars. So for English, there's only the ED rule. Right? There are no other rules at all in the system. And all of the remaining forms that can't be derived by that one single rule are derived by an associative network. If you take the theory in its strongest terms, this would imply the following. Only irregulars are lexically listed. Right? The others you can derive by rule. Moreover, the associative network is only needed for irregulars. It doesn't derive regulars. That's what I take to be the strongest version of the theory. Classical connectionism goes just one step further, saying that there are no rules at all, and that everything is derived in the associative network. Well, what do we think? Based on our experience, if the problem of learning rules amid exceptions is taken seriously, and Pinker and Prince's proposal is suitably altered, what you get is a very detailed, very large grammar. And this grammar can derive with pretty good, pretty accurate well-formedness ratings. Quite a few of the forms, like splang, that are attributed in the other two theories to analogy. And indeed, if you think about Pinker and Prince's proposal, it starts to look a little bit odd. As I mentioned earlier, all the rules of non-maximal generality are discarded at the end of the learning process. And the work that they might have done for you is undertaken instead by the associative network. Do we really need to do this? Maybe the learning system in humans is profligate in its labors, but maybe not. So that's the scheme. So looking at 46, one might reduce the various theories in question to the issue of where is the boundary between analogy and rules? If you look at a continuum of extreme detail on one side and extreme generality on the other, the dual mechanism model puts the boundary, let me do it by your orientation, right near the edge. So there's only one rule. Connectionism puts the boundary all the way over the edge. There's no rules at all. We'd like to consider the possibility that there's more than one rule, and that these rules can enter into the range of detail that one sees in the middle. 47 basically summarizes opinion of quite a few other linguists. If you read, for instance, a recent issue of Behavioral and Brain Sciences with an article by Clausen, who's an advocate of this theory, quite a few people replied, and these people were linguists who were upset that the nice generalizations that they had discovered and reduced to rule that work for, in this case, German, were not being taken into account by this theory because you could only have one rule. Their contention is that language is more complicated than that you can have, I'm sure linguists will sympathize. Moreover, rules can do fancier things than just add an affix. There's all sorts of wonderful stuff out there. Derivation by deleting material, derivation by copying it and preposing it somewhere in the middle. There's a lot of really good stuff, and linguists like to study it, and we want it to remain rules. So that's what we're rooting for. That's the prejudices. If you want to find defaults, it probably won't work just to say that a priori that they have to be simple. The languages might not accommodate you that way. Next point concerning the dual mechanism theory is the question raised in 48. Would it be possible for more than one rule to derive regular forms? Our grammars have lots and lots of rules, all of which inflict the regular change on the stem. Could some of them be legitimate, or do we only take the most general one? That's what is at stake. To make sense of this, let me define a term. An island of reliability is a phonological structural description that isolates a set of forms in which a structural change applies with greater reliability. Now, everyone who's looked at these past tenses agrees that if you're talking about irregulars, the new forms will be generated only if the stem falls into an island of reliability. So if you're going to get splung, it's got to be a verb that has I before a nasal and hopefully a liquid. It's got to fit that island. But much more controversial is the question of whether there could be an island of reliability for the default outcome, for regulars. Well, the lexicons of these various languages certainly provide some candidates. In English, for instance, if you have a short vowel followed by a final P, all 19 verbs that fit that description are regular. And our learning procedure takes this into account into the scores that it would assign to the relevant rules. The rule for short vowel P has a score of 0.967. The context-free rule that attaches ed anywhere is 0.910. Likewise, and I won't go through them in detail, but in Italian, min is an island of reliability for the regular conjugation, first conjugation. In Spanish, e before a k is an island of reliability. E never diphthongizes before k, and there's 27 examples. All right. Now, what about empirical data? Do native speakers behave differently in a WUG test when the form that they're looking at is in an island of reliability? The best case we have so far is from Adam Albright's work on Italian. He craftily arranged his WUG test in advance so that it would include some WUG stems that fall into islands of reliability for Italian and some that wouldn't. He did it in an obvious way. He used the learner in advance to find these forms. Okay. Now, here's some of the data. For WUG forms like guarminare, veggeggiare, fraquinare, which are in islands of reliability, the consultants liked them quite a bit better, and the grammar, of course, liked them better as well. Whereas forms like adungare, funadare, shinkadare, the grammar didn't like them as much, and the consultants didn't either. The correlation of the learner's opinions with the consultants, if you consider are forms only, so we're just talking about the regular outcome, you get a correlation of 0.48, and that's significant. Worth mentioning that a pure dual mechanism approach would use the very same rule to derive all of these forms and would predict they should all sound exactly as good as each other to Italian speakers. Similar results we think we have both on English and on Spanish. I'll skip 53 and go on to 54. What is our take on the dual mechanism approach? First, the idea that those forms not derivable from the default, only those forms receive lexical listing, is something that is falling to experimental work right and left now. And Pinker, in his recent book, pretty much revises the theory, so it abandons this prediction. Second bullet, there is only one default rule per morphological process. All else is analogy. We and quite a few other linguists think this is not right either. The default rule serves as the only mechanism for deriving regulars. I've just given you evidence that that one is probably not right. Is this a dead theory? Well, hardly. There's one claim that is still there and is actually the central claim of the theory, that there's both a lexicon and mechanisms for deriving new forms. And indeed, Pinker is now labeling the theory the words and rules theory, perhaps in recognition of this. It's a little bit hard for linguists to imagine, but this is an ultra-controversial hypothesis. Many connectionists feel that the distinction between lexicon and grammar is completely illegitimate. So the point is still being debated, and quite a bit of experimental work continues to be carried out to try and decide this question. So we think it's a live theory, and suitably amended, it's a theory that we feel rather comfortable with. Connectionism, I have very little to say about, only to make what I hope won't seem like a snide remark. From what I've read, it seems that the performance of connectionist simulations improves as the linguistics gets better. If you have representations that have things like segments, features, a preference for copying stems, a lexicon versus rules, which you can do in connectionism, performance seems to improve. And in fact, this holds for us as well. I mentioned that the linguistics in our model is presently very primitive, and we think that we can improve the model by improving the linguistics. So one might hope for parallel development of symbolic and connectionist simulations, gradually improving the performance of both. Last little bit. Can I close with something really empirically speculative? There we go. It's an experimental result that's very new, and we're sort of taken with it, but of course it's also very tentative and amenable to alternative interpretations. But it bears sort of on the heart of what I'm trying to get at. You'll recall that where we differ with other theories is where we want to put the rule analogy boundary. We want there to be lots of rules. We think there probably is such a thing as analogy, but it's not clear how important it is in grammar or in the behavior of speakers. So let's think for a minute about what does it mean for something to be a rule? What does it mean to be an analogy? If you're going to have a rule, this is 56, you first learn a grammar. And you learn a grammar by looking at a bunch of forms. You find what they have in common, and you abstract from them a means of creating new forms. Then, if you want to create a new form, you look up the relevant rules of the grammar, and you apply them if you can. Analogy is very different. To do analogy, you find an analog form, or perhaps more than one, that is closely similar to the base, and you change the base in the same way that the analog was described. So spling, splung is done presumably the very same way as spring, sprung. All right. Now, this could, in principle, lead us to an empirical claim. What about analogies that are based on one single analog? There are plenty of them in English, because English has such bizarre irregulars. Could bring, brought, which is unique, spawn, spling, splot? That's the question. We, I think, can safely claim that rules could not generate spling, splot, or more, I have to be a little bit more careful. Rules involve generalization over forms. Okay? And we find that setting the only really adjustable parameter of our algorithm, which is the lower confidence limit, anything based on one form, you do get sort of a pseudo-rule, but its value is very low. So I think it's reasonably fair to say that our system says people should not volunteer forms that require a single form analogy. Is the distinction clear? Well, as I said, we have a WUG test in progress. And in setting up this test, we had a number of goals. one of which was to address this very question. We have included WUG verbs that are in islands of reliability for irregulars, and that might rate highly as irregulars by virtue of a semi-general pattern. So we put spling in there, because it matches a number of verbs. We also put in some WUG verbs that might rate highly as irregulars by virtue of close resemblance to an existing highly frequent irregular. I'll give you some in just a second. Our consultants so far were mixed. We asked 6 linguists to take a very hard test. Namely, we forced them to volunteer irregulars. Right. That turns out to be excruciating, and they started to hate us, and then we stopped. The 18 happier consultants were UCLA undergraduates, and they were permitted to volunteer whatever they wanted, including regulars. And indeed, we were rather struck by the fact that they mostly volunteered regulars. A number of them answered for all 60 WUG verbs. They gave the ED form. It was a very serene but slightly boring experience for them. Okay. The irregulars were rare in general, about 9%. Filtering the data in a way that you can read about in the footnote, but I lack time to explain, let's look at the cases that were volunteered by at least 3 consultants. Here we go. 60 are forms where learning could be based on at least 2 and usually 3, 4, 5 existing forms. Dies, does, fleep, flept, gleed, gled, queed, qued, spling, splung, spling, splang, buys, bows, fro, fru. Things where you can find a number of analogs in the language. For most of these, the learning algorithm finds all of these analogs and finds a rule of limited generality and is willing to assign a reasonably good score. These are also the ones that are characteristically volunteered by our consultants. On the other hand, we also included the following in 61. Kiv, where you are invited to respond with cave. Lum and pum, where you're invited to respond with lame and pain. Today I she, yesterday I shaw. And today I knolled it, yesterday I knelled it. Now, these were volunteered from time to time. But here's the part that strikes us as perhaps not convincing, but at least tantalizing. From the free choice subjects, the ones that had the option of volunteering a regular, not a single one volunteered anything like she, shaw. They were only in the forced choice guys. Okay, so what's going on here? We would like to think that our WUG test is the most natural WUG test that has ever been inflicted on people. You hear rather than read the WUG verb. You use it in, Stephen Wilson wrote very charming little dialogues. So you use it in a lively, engaging colloquial dialogue. You practice it, you hear it or practice it 3 times before you fill in the crucial blank. You never get an irregular modeled for you. We think once you start doing that, people will get creative and start forming irregulars like crazy. So, in a maximally naturalistic condition, it would appear that forms that have to be analogy were not volunteered. That's the very, very tentative result, and if that holds up, maybe that's something that is meaningful. So the interpretation in 62, if this is right, analogy, insofar as you can clearly diagnose it in the cases of single form analogies, is perhaps not all that it's cracked up to be. People will do it if you force them to arrive at a past tense, but they may be less likely to do it under maximally naturalistic conditions. It is the minor rules, based on at least 2 and usually more learning data, that naturally lead people to project novel forms. So if this is right, something along these lines pursued with more data, this could be the way to get at the rule analogy boundary in
Actually, a question. you have any reason to believe that when your subjects heard kid, that a word that came to mind was give as opposed to live, or that when they heard she, that the word that came to mind was
We tried to maximize the possibility that this would happen by picking the most frequent models that we could. And of course, the more subjects that we run, the more we can rule out the possibility that.
I mean, you could easily test S then, you know, in a large task. What, I mean, a large body of numbers.
If the
analogy
Yeah.
Form is not ranked very high on your list of items, then it's not expected to.
Our experience elsewhere is that people are surprisingly bad at telling you what the analogy form is. This process can be surprisingly unconscious. All right, last little bit. Obviously, this is very tentative. We continue to revise our model and to test it against data. But the last bit that I'd like to say is that I think progress is likely to come especially from comparative modeling. If we reach if we have something like what DARPA apparently already does for speech recognizers, the very same model is applied to the very same data. That if a research program gradually were developed in which competing theories looked at the very same sets of learning forms and WUG task judgments, we think that such comparisons might be very fruitful. We're hoping to at least participate, if not initiate such a program, by posting all of our learning sets and WUG test judgments on the internet, and we encourage other people to do the same thing. Okay, thank you. Ask all the questions you like. Yeah, Peter.
To sort of follow up on Bill's question first, it seems to me one way you could get at his point would be to simply take a look at the token frequency of the different forms there, and to see if you have something that is wildly out of kilter for one of the forms. So in other words, if it turns out that the token frequency of give is much higher than the token frequency of live plus all the other forms that form an ED thing, then you have a stronger grounds, it seems to me, to argue that they actually might be pushed in that direction.
Yeah,
right?
That's a nice idea.
So that you could drive it that way. Then the only other thing I wanted to say, which is a little bit different, is that it seems to me when you raise this issue about analogy and rule learning, I guess I have to wonder to myself if you could even try an analogy if you didn't already have some sense of the notion of rules. And the reason I say that is because it seems to me that in order to form an analogy, you have to already make some assumption that there's a regular relationship between two forms.
Huh.
And you're going to then import that relationship, in a new context. So it might be, even if it's just the sense that there's a regular pattern here between this one form, present form, and one past form, or something of that sort, right? You've already sort of inferred that, there's a regularity there, and now I want to use this regularity to now put it into another context.
I've always felt that way myself, that there is no such thing as pure analogy. You need a little bit of rulishness to describe structural change. So if you're going to have this is the sort of ruly part that you need to get kiv-cave. Now, if you want to have all rules, then you start putting in a context here. And so, it's a formal rule that has a structural description and matches up and so on. The analogy part can only consist of saying, give-gave has this structural change and is phonetically similar in some gestalt-like overall way to kiv. So yeah, analogy is relevant only for finding the structural description part of the story. Yeah.
I was wondering, what is connectionism? I mean, is it that a circuit can do it, or is it that a circuit which is completely random can learn?
Yeah, that's a good point. And
Because surely a circuit can do anything, including these exceptions, etc. I should first, list all the exceptions, and that's thrown in that direction. So what does connectionism mean?
It's a hard question to answer because there's various kinds. I mean, let's first state the obvious. Connectionism is true. All we have is neurons and synapses. So somewhere in there, it's all done with a neural network, a literal physical neural network. The real debate revolves around whether it makes sense to speak of this neural network as carrying out a computation of the kind that a linguist might feel familiar with. That is,
It would be called not computing. Then it would be called.
well, no, there's different names for it. Maybe
or then it would be not
did you invent these names? There's eliminativist connectionism and implementationist connectionism. If it's implementationist, it means you take the neural circuitry and you use it in some way not yet understood to implement symbolic rule systems. The eliminativists would say, no, the rules are simply illusions. They are compact. I think Prince and Pinker write this. They are compact notations to reduce the data, but the rule system, that the mental system that's inside the brain of the speaker, we would never, ever recognize anything like the linguist's constructs in there. And the debate seems to be between implementationalism and eliminativism. Yeah.
And just directly on that point, I want to thank you, Professor Hayes, for this fascinating talk. But I would like to take it as you have proposed a great connectionist model of the past tense morphology debate. And the reason I think your model is a connectionist model is because the generalization step, when you have some data and you formulate simple rules and then you generalize lots of simple rules to one general rule, works just the same way as the Hebb rule in neural nets. And the generalized rule is exactly the increased force of many places where it could apply correctly. And so in a sense, what I didn't understand before when I was snarfing that what rules do you get rid of, what I didn't understand is that, and I think I understand now, is that all your rules apply in parallel all at once, and that then you look at the probability distribution that the network, if I may say so, produces, and then you compare it to human performance. The general rules are always, for a given form, lots of general rules will apply by definition because the structural environments are so general, but fewer specific rules will apply because by definition the structural environments are more specific. So you have a whole mountain for new forms, if they're regular, or if they're in an island of regularity, then a whole mountain of micro rules will apply, including the general ones, and the specific ones. In the areas of non-regularity, only the very general ones will apply, and that sort of implements analogical productivity. So anyway, I think this is a great connectionist model, and I applaud you.
Cool question. First of all, thank you for your kind remarks at the beginning of the question. I hope they don't diagnose you're sizing me up as paranoid about questions.
Not at all.
Okay, thank you. Let's see. Are we connectionists? You're not the first to call us connectionists. Well, Adam Albright, my collaborator, has called us connectionists. I think
you're sub-symbolic connectionists, too.
No. No, that's a cruel blow. Okay. But no, I think I can actually maybe say something in response to the question, which is a good question. Linguistics, as Janet Pierre-Humbert has pointed out, has been strikingly reluctant to make use of continuous mathematics in any form. Right? It's always been discrete mathematics. And she has a big problem with this, and I think I basically agree with her. So surely we've got continuous mathematics here in terms of the evaluation metric for rules, which is a real number. On the other hand, there are differences that might be diagnosed here that are based on our ability to use symbols in the rules themselves. In fact, this is a model I feel really comfortable with, and I've worked in other papers where you've got rules and constraints, but they are coupled with a quantitative structure. So part of the model is categorial, because language strikes me as kind of categorial. But where language is gradient, like people's judgments of rival WUG forms, we ought to import the continuous math. Now, here's what is perhaps the really crucial thing. And I think it's something that drives performance of these learning systems in a really important way. It is the ability to include variables in rules. That a rule like this is going to play a major role in systems. It plays a major role in various ways. So maybe worth comparing this with a less rule-oriented system by, it's on the handout, Ling and Marinoff, who used an off-the-shelf learner to do past tenses. Which doesn't have variables. If you have a variable, you've always got this thing to back you up. It's going to have a pretty good score. Not as good as the islands of reliability, but it will always be there to back you up. Thus, if your schemata cannot look at more than 3 syllables worth at a time, which is true in some simulations, this will always give you the right answer for a quadrisyllabic verb. If your schemata include only the phonemes of English, it will be able to derive the past tense. This is from straight out of Pinker and Prince. Telemann outbacht Bach. Okay, the things that aren't even in the phoneme inventory, people know how to inflect them. And if you look at how Ling and Marinoff's system behaves in WUG testing, you get cases where it fell into a trap because it looked at a special case and did not have the general case available. So, I speak in pretty serious ignorance of connectionist systems and what they can be made to do. But certainly in the literature, guys working on symbols have said that the most powerful weapon in their inventory is the variable. That's what you need to have a true default. Yeah, Paul.
I thank you for giving a lovely talk, very stimulating. But I really have a problem with the decomposition between the rule, between handling existing lexical forms one way and handling these novel items a totally different way, right? Yeah. So is the claim that all lexical forms are completely memorized and there's nothing psychologically corresponding to rule-based phonology at work in generating or processing or in any way using lexical items, and it only comes into play for non-lexical items? Is that part of the bigger picture or not?
It has to be part of the bigger picture.
But it has to be wrong, right? Doesn't it?
No, I think we are not obviously wrong. Or I wouldn't be here, right? Let me tell you about this wrong theory we invented. We're not obviously wrong as a theory of what you might call the mapping component, the synthesis component. People have this ability to generate novel past tenses or whatever. They have the ability to pass WUG tests, and we think that modeling that ability is a fascinating challenge. But obviously, that can't be the whole theory of people. Here are some things that we think ought to be explained. There's all these wonderful psycholinguistic experiments trying to explicate which forms actually do get memorized. It appears that the forms that get memorized are irregulars, high-frequency regulars, and regulars to which the rules for irregulars might apply. So ping. To keep ping from becoming pung, you've got to list it. Pinker has suggested what seems like the right story here, that you list that which you cannot safely derive. That might be a gradient notion. So that might be a way of extending the story for what gets listed in the lexicon. But there's more.
I understand, because the regular, according to the Pinker view, it's the regulars that should be produced by the rule system, right? And you've got a whole bunch of rules here that produce what might actually be called analogically created irregularizations and regularizations for novel forms.
Yeah.
But you haven't given us any rule system at all for regular lexical items, or irregular ones for that matter, right? That's outside the system, you said.
Rules for regular lexical items.
Right. I mean, somebody asked the question, won't you predict from this story that for regular lexical items, like spring, people will sometimes say sprang and sometimes say spring and sometimes say sprung or whatever, in the same way they do with spring, to which your answer was, well, they've memorized the lexical items, from which I inferred that the processing of lexical items is not by this rule system, but rather by the memory system. So it's exactly the opposite of the Pinker picture, where irregulars are all about memory, regulars are all about rules. Here, on your story, regulars and other lexical items are all about memory, and it's only novel forms that are about rules, if I understood it right.
Or the challenge, the ones that might look like irregular, not to be subject to the rules for regulars. Were you saying that your claim is that you needed to store regular past tenses if they looked like the kinds of verbs that might be derived by irregular?
Yeah. Look, what is needed is a number of theories, most of which would be theories of processing rather than of grammar, that would address issues like, under what circumstances do you say a word by extracting it from your lexicon and uttering it, versus extracting, say, the stem and applying rules and uttering the result. And by now, there's quite a bit of psycholinguistic evidence that could bear on the construction of those theories. Moreover, at the level of learning, we have sort of the opposite problem. You hear a new verb in the past tense. Do you decide to ensconce it in your lexicon with a new entry? Or do you say, hey, that's jumped, I know jump, I can synthesize jumped, I won't bother. So these are questions that a psycholinguistic theory of processing would address and hopefully successfully resolve. My current guess for what's basically right with these theories is, first, at the level of learning, the strategy is pretty much as Pinker said. If you are already able to synthesize a form safely, say above 0.93, if you're able to synthesize it safely, then you either don't install a lexical entry or you install a rather weak one. This would imply, given the numbers that our simulation is producing, that every single irregular would be stored.
And what about the regulars?
Depending on where you set the threshold, it would imply that they call them pseudo-irregulars, things like ping, are going to get stored. And one must remember that the child has to begin somewhere. We assume that in order to get the system up and running, the child puts lots of memorized forms on the workbench and ponders them. So those frequent verbs that you hear earlier in life and you use to set up the system, they must be stored as well. And from my relatively casual knowledge of the psycholinguistic literature, I think something like this is fairly realistic. On the production side, the model that we find our most congenial is, I'm going to show my weakness with the literature here, but they're so-called race models, where you let synthesis of the novel form from the present stem occur in competition with the process of extracting a memorized form from the lexicon, and that you'll get a sort of time course over which they compete. Usually, of course, a listed form will win, but since even adults occasionally over-regularize, it shows that it was in competition with the synthesis process. So those are the two chunks of the psycholinguistic theory, or at least sketches of them, that I think this model could be embedded within to make a more complete account.
I wonder if the kinds of psycholinguistic data that's been used to argue for, say, whole word storage of regular forms is as transparent in its support of that position as you want it to be. The kind of data have to do with whole word frequency effects in recognition and in the relative the fact that they're relatively insulated from error. High frequency forms are relatively insulated from errors in production. Now, it's true that the more often you produce a form, the less likely you are to make an error producing it. But I find that when I go to a conference, if I practice the talk many times before I give it, I'm less likely to err in my execution of it as well. And I'm not sure that I'm prepared to say that when I produce the sentences that comprise the talk, that what I'm doing is I'm recalling the sentence forms in all of their splendor from memory. What I've got is something that enables me to pursue the compositional procedures in a rather efficient and less error-prone way than if I hadn't practiced the talk. But it's not obvious to me that I want to make a case that the fact that I've improved my performance by producing the same sentences or the same approximations of the sentences, it should really be taken as evidence in support of say, a whole sentence storage theory of talk production. And so I wonder if we might consider this as undermining the type of support that you're leaning on. Standing on? If I practiced that, I would have had a better. If I practiced the question, I would have had a better.
This is a very interesting question, and I'm tempted to answer it in conflicting ways. One line would be to suppose that my knowledge of the verb, think of a frequent regular, suppose that's there in my memory traces. Right. Play. Yeah, frequent for children too. Okay. Suppose that's, I did a lot of playing in the late 50s and early 60s, and it's ensconced and it's permanently there. Okay. So, whereas my ability to give this talk as fluently as I just gave it is going to go away in 2 weeks. So that would be one line that one could sort of experimentally verify, that somehow the...
That may be, but I wonder, what type of representation you're positing for this model. Whether it's
Okay, well, now let me try to answer the question the other way that I wanted to, which is to tell you a charming story told to me by David Perlmutter. He was a native speaker of Yiddish up to about age 7, and in fact became literate in Yiddish. And then changes in family circumstances cut him off from the language completely. He can sort of, speak Yiddish now. And then recently, I guess, clearing out a grandmother's possessions or something, he ran across a book in Yiddish that he had read when he was 7, which I don't know how David is, but we're talking, maybe half a century or something. he recognized all the sentences and he thought, this is where I learned this word. So he claims to now what is special about this is that you and I have had the sentences in the books we read as children overwritten by vast amounts of English that we have encountered since then, whereas David Perlmutter's Yiddish experience was allowed to sit there pristinely. Okay, so that's maybe a silly anecdote, but you know, there are guys who are enthusiasts about really extravagant theories of memory, right? The guys who believe in episodic memory and so on, and I lack expertise in this, but who am I to say that people don't have, you know, pretty good traces of a lot of regulars?
Well, my first question, I mean, for David, who had been so nefarious as to actually substitute a book that changed many of the sentences in that book, I doubt that he would have detected any of them, because there's lots of experimental evidence that shows that even across the such long periods as, you know, the duration of an intervening sentence, we're not very good at distinguishing sentences that we had heard from sentences that we hadn't heard that convey the same information.
Yeah.
So, I mean, it's true that we can bring forth all sorts of memories from various types of experiences that give us the impression that we have accurate memory. But there are lots of people who would point out that that's probably much of an illusion.
Yet there are data that show like age of acquisition for particular vocabulary words are predictive of behavior in some kinds of tasks. So Amanda Wally has done a lot of stuff going back using that measure to sort of get an idea of what kids' lexicons are like at various ages. And some of that holds up. You know, now I was wondering in your case with play, if one would make a prediction that things that are early acquired like this, like play and played, would actually behave differently from words that you knew people acquired much later. I mean, if your story goes through with respect to, you know, storing some of those forms then one should expect to see those in early acquired vocabulary items, but perhaps not so.
It wouldn't be hard to test, because the forms that are frequent for little kids are not exactly the same as the ones that are frequent for adults. So if lifelong experience determines frequency, it'll be a different set from the ones that were our favorite verbs when we learned past tenses.
Well, yeah, that's true, but you can actually do these age of acquisition things with adults, and they actually are fairly accurate about when they have. I mean, that's the interesting thing. They're fairly accurate about when they have.
I think we have to end here. Thank you, Bruce.